This section introduces the core problem, determining the accuracy of statements about scikit-learn's BallTree algorithm, a method for finding nearest neighbors in data. We're given a scenario with 10,000 data points in 3 dimensions, and the task is to identify the 5 nearest neighbors to a new data point using BallTree. The statements we'll evaluate test our understanding of BallTree's efficiency and its relationship to data size and dimensionality. This sets the stage for the quiz. We have a specific scenario: 10,000 data points in a 3-dimensional space. The algorithm BallTree in the scikit-learn library is used to find the 5 nearest neighbors to a given point. This provides a concrete context to evaluate the statements in the following lines. Statement A claims BallTree is always faster than brute force, checking every point. Is that always true? We'll explore this considering the number of data points, 10,000, and dimensions, 3. Statement B asks, does the time BallTree takes to find neighbors depend on the number of data points, 10,000? What's the time complexity relationship? Statement C is factual. BallTree uses a tree to organize data for efficient searching. It's a core design feature. Statement D explores BallTree's performance with increased data dimensions. Does adding more dimensions help or hurt efficiency? The curse of dimensionality plays a role here. This is a title hinting at the underlying data structure. The efficiency of BallTree depends heavily on how this structure is designed and organized. This section introduces the core problem. We're using a BallTree, a specific algorithm for finding nearest neighbors, to search a dataset. Think of it as a super efficient way to find the closest points to a new point in a large dataset. Imagine you have a new data point, a single entry, that you need to place within the existing dataset of 10,000 points. We need to find its closest neighbors. The K in K nearest neighbors refers to the number of closest neighbors we want to find. In this case, K equals 5, meaning we're searching for the 5 points in our dataset that are closest to our new data point. Okay, so this question is about scikit-learn's BallTree algorithm, a powerful tool for finding the closest data points. We're dealing with a dataset containing 10,000 points in a 3-dimensional space and want to find the 5 nearest neighbors to a new point. The quiz then asks which statements correctly describe BallTree's performance and properties. Statement A claims that BallTree always outperforms a brute force search. While BallTree is generally faster, especially with large datasets, it's not always guaranteed. For very small datasets, brute force might actually be quicker. So, this statement is too strong. Statement B says that the time it takes to query the BallTree is unrelated to the dataset size. This is incorrect. BallTree's efficiency is linked to the number of points. In the best case, it has a logarithmic time complexity, which means the time increases slowly with the number of data points. In the worst case, the time complexity is linear. Therefore, this statement is false. Statement C says that BallTree uses a tree-based structure. That's absolutely correct. It's a core part of how it works. BallTree partitions the data space into hyperspheres using a tree to efficiently locate nearby neighbors, making it much faster than comparing every single data point. Statement D says increasing the number of dimensions improves performance. This is incorrect. The opposite is generally true due to the curse of dimensionality. As dimensions increase, the efficiency of tree-based methods like BallTree drops. Therefore, this statement is false. This refers to the core algorithm we're using to find the closest neighbors in our dataset. It's like having a super efficient search engine for points in space. It cleverly organizes the data into a tree-like structure to speed up searches. This sets the stage for our problem. We're using a specific tool, scikit-learn's BallTree, to solve a common machine learning task: finding the nearest neighbors. We are given a specific context of a large 3D dataset and the goal to discover the 5 closest neighbors. This gives us the size and dimensionality of our data. Imagine 10,000 dots scattered in a 3D room. Each dot is one of our data points. We have a new point, a new dot, added to that 3D room, and we want to know which existing points are its nearest neighbors. The K in K nearest neighbors is 5, meaning we want to find the 5 dots closest to our new point. This line reinforces that the BallTree algorithm, a specific type of tree-based data structure, is what we will use to find those 5 nearest neighbors. Okay, Vamsi, so we're dealing with a k-nearest neighbors search problem using BallTree. We have a substantial dataset, 10,000 data points scattered in a 3D space, and we want to efficiently find the 5 closest neighbors to a new point we've just added. The efficiency and the method are really the heart of the problem. This statement is tricky, Vamsi. While BallTree is generally faster for large datasets and higher dimensions, it's not a guaranteed win. For smaller datasets like this one, relatively speaking, the overhead of building the tree might actually make brute force faster. Let's keep that in mind. This one's false, Vamsi. The time it takes to search using BallTree does depend on the number of data points, albeit not linearly. In the best case, it scales logarithmically. That means the search time grows proportionally to the logarithm of the number of data points. It's much more efficient than a brute force approach where search time grows linearly with the dataset size. This is absolutely true, Vamsi. That's the whole point of BallTree. It cleverly organizes the data points in a tree structure. Think of it as a hierarchical organization of hyperspheres, to quickly locate nearby points. This is its secret weapon for efficiency. Nope, Vamsi, this is where the curse of dimensionality comes in. As the number of dimensions increases, the effectiveness of BallTree, and many other spatial data structures, decreases. Imagine trying to efficiently search in a high-dimensional space. It becomes increasingly difficult to define hyperspheres that effectively separate data points. Therefore, the performance will generally degrade. This is the core problem statement. We're using scikit-learn's powerful BallTree algorithm to efficiently find the closest neighbors among a large dataset, 10,000 points in 3D space, to be exact. We want to select the true statements about how this algorithm works and performs. It's all about understanding the BallTree's strengths and limitations. That's correct. The BallTree's name gives it away. It uses a tree-like structure, similar to a decision tree, but optimized for fast nearest neighbor searches. This structure allows it to efficiently eliminate parts of the dataset that are far from the target point, making the search significantly faster than comparing to every single data point. This specifies the size and dimensionality of the dataset. We have 10,000 data points, each represented by 3 coordinates, 3-dimensional space. This large number of points is where the efficiency of the BallTree really shines compared to brute force methods. This is the specific algorithm used for the nearest neighbor search. The BallTree isn't just any tree. It's specifically designed to speed up nearest neighbor searches. This is the heart of the solution. The problem wants to find only the 5 closest neighbors. This is known as the k-nearest neighbors problem, where k is 5 in this case. The BallTree is particularly well suited to find the k-nearest neighbors efficiently.